Whoa.
Hi. We have a new setup today because the internet has been terrible this morning. So we are using my phone as a document camera. Can you see my can you see the printer paper?
Yes.
Yeah. Is that your son?
That was my son and my son-in-law were helping me. I have two top-notch IT people here. They're both in computer science.
Nice.
So I was panicking. I have a pre-calculus class this morning, was disaster. During the whole time the internet didn't work basically. So I have to switch to this document camera, which is just my phone. Okay. So what I plan to do today is so one application, okay? Because we have learned enough of the stuff, we can do this application and hopefully so that you can appreciate a little bit more about linear algebra. This is not going to be on the final, so don't get too stressed out about this, okay? There's no homework assigned to this, but it is good since we are getting so close to be able to understand this type of stuff. So over the weekend, I decided to prepare some stuff. It's called principal component analysis. Okay, so you guys can see what I write? Can you guys see it okay?
It's okay, but could you write a little bigger?
Okay. I will write a little bit bigger. No problem. Oh, you saw me? So you saw me using, this is because using the QuickTime or just my camera? Okay. Okay, we zoom in a little bit more now. So are the words better now? Eva?
Yeah.
Okay. I'll write bigger, okay? So this example, it's basically using this example to develop so that you get a better understanding of this thing called principal component analysis, which is using eigenvalues and eigenvectors and all this stuff, okay? But you do need to know a little bit about statistics, okay? So we start out with this. We have a bunch of boys. Five boys, okay? Each of them, you record the weight and height. We're going to eventually generalize this to facial recognition. Exactly the same setting, okay? Except that instead of there are 2 entries, it will be 10,000 entries. Okay, so instead of 2-dimensional stuff, it will be 10,000 dimensional. But this is going to be smaller example to make it a little bit easier for us to understand the procedure and for us to compute some stuff. Okay, so this the weight in pounds and the height in inches. Of course, the weight and the height are correlated. Correlated means that somebody who's taller probably will weigh more, usually, but not all the time. Okay, usually that is the case. So in that case, there's a correlation between the two. So you compute the mean, 130 pounds, and the mean height, 65 inches, 5 feet 5, for this set of boys. Now this can be represented as a matrix. You have this matrix here. Okay. Now the matrix we are interested in is this matrix here. Okay. It's the matrix which is the deviation from the mean. Is the handwriting readable now or not? Eva, is it readable now or?
Yeah, it's okay.
All right. Okay. So now I do a subtraction. So 120 subtract 130, so it's minus 10. 125, you have minus 5, minus 5. This is going to be 5 and 15. You guys understand how I got this second matrix? Now this second matrix is called B. Okay. So this is the deviation. Okay, feel free to ask questions, guys. Otherwise, I'm going to just keep going. This is the deviation from the mean. Mean means average. You add this guys up, divide by 5. You add this up, divide by 5. You get these numbers. You get the deviation from the mean. Now we have this new matrix. So we have the matrix B now. This matrix S is 1 over n minus 1. N is equal to 5. In this case, there are 5 boys. Okay. B transpose. Okay. I need to show you what that means. So this will mean 1 over 4 because n equal to 5. This is my B. And this will be my B transpose. Then you get some matrix. Okay. You get this matrix. What size of the matrix that we are going to get? What is the size of the matrix we're going to get?
2 by 2.
2 by 2. Very good. It's a 2 by 2 matrix with 100 here, 25 here, 47.5, and 47.5. Now, this matrix is going to be symmetric. A bunch of things I want to talk about this matrix. This matrix is going to be symmetric because S is equal to this, right? So what would be what would be S transpose? S transpose will be 1 over n minus 1 B transpose. The transpose of this guy is going to be this transpose, B transpose, which is over n minus 1.
I can't see you writing.
Because I'm writing, it's better now. Is it better?
Yeah.
Okay. B, okay. I have this one in the wrong place. B transpose. Because you have to swap this order when you do the transpose. Okay. Is it all right? So S transpose is the same as S. Okay. This is the same as S. So S is symmetric. All right, so we have a symmetric matrix. So I also want to show you that this guy here, this is actually the standard deviation. This is a variance. This is called a variance. Variance is the same as standard deviation. So this is the part which is you need a little bit of statistics. So this is the variance of the weight and variance, weight variance. And this guy is the height variance. I mean, if you understand the definition of variance, is basically the square. So it's this term, right? This term is the deviation. This multiplied by this. Okay. So it's the square of the deviation. And then you add them up. Okay. And then you divide by n minus 1. And that is the variance. So you get this dot product here. Okay. You get the terms for the variance. This other one, you get the terms for the variance. So how about these other entries? These other entries are called covariance. Okay, this is called covariance between weight and height. So how much are they correlated? Okay.
Why? I have a question.
Okay.
Why is it n minus 1 instead of?
Go ahead. Oh, instead of n, I can talk about it a little, just a couple of sentences, but you have to do your statistics class. Because it's a sample, if it is an entire population, they divide by n, you get the variance. Because it is a sample, you have to divide by n minus 1. So you can get a so-called unbiased estimate. Okay. So that's all I can say at this moment. Okay. So if you do your, I don't know whether you have taken any statistics class or not. Have you, Eva?
No.
Okay. So it makes sure this is a little bit deep in terms of mathematically if you want to prove it. Okay. So now we get this S here. Now this is a symmetric matrix. Okay. Since it's a symmetric matrix, I can actually do the eigenvector and eigenvalue. So the way that I'm going to do this is that I won't go through all the computation because I want to show you the eventual result and what is we are going to be able to achieve. Okay. So S is symmetric. I'll basically prove it to you earlier over here. Why is it symmetric? Okay. So because S is symmetric, so S is orthogonally diagonalizable. Okay. What does that mean? That means S can be written as P transpose, okay, and with some value of P, some function, not function, some matrix P and matrix D. So these guys, this P and D are related to the eigenvalues and eigenvectors. Is that right? So this particular example, the two eigenvalues lambda 1, these are the two eigenvalues. Okay, and the two eigenvectors corresponding to these eigenvalues are this. I am not going to go through the process of computing it because we want to save some time. Okay, and also don't want to get too bogged down in the computation. But it's hopefully it's not too difficult for you to understand. You guys understand the procedure for getting eigenvalue and eigenvector because it's a 2x2 matrix. It's not too difficult to do. Okay, you do this determinant S minus lambda I equal to 0, then you get lambda 1 and lambda 2, and then you solve it for the eigenvectors. Okay, so what will be D and S then? Now my S is going to be equal to this one formed by V1 and V2, right? Will be this guy, 0.9, 0.436. What will be D? Can somebody tell me what is D? D consists of, it's a diagonal matrix with the eigenvalues as the diagonal. Okay, so we get our D and the S. Sorry, this S is a P. It's the P. The S is the original matrix. I wrote it wrong. S is the original matrix. So this is my P. So S is now PDP transpose. Okay. P. D. P transpose. So this is my S now, PDP transpose. I'm going to do a change of variable. Okay, so the change of variable is y equal to p tx. We did the same trick before, the change of variable when we do the quadratic forms. So it's a similar thing. We do a change of variable. The main thing about this is that we do a change of variable and we are going to be able to decorrelate, okay? So that we will end up with something, two directions, okay? Which will have explain the variation in the data. We will draw some picture for you later, okay? But I'm going to just keep going unless you have questions. So we do a change of variable. Now, what does that mean? That means we have two new variables, y1 and y2, okay? And this guy will be the P matrix, okay? This is my P matrix. P transpose is going to be this guy. Times x1, x2. Okay. What does this mean? That means y1, this is my change of variable, is equal to x1. Now remember, x1 is the weight and x1 is the weight and x2 is the height. Okay. Now, with this change of variable, okay, with this change of variable, we are going to be having a new covariance matrix. Now, original, you have a matrix B, okay, and the covariance matrix is S equal to 1 over n minus 1 B transpose. But now I have a new matrix. So this is the transformed matrix, okay? New matrix, okay? So instead of B, okay, because for every entries, the original table. For each of these guys, these are the x values, x1, x2, x1, x2, okay? I'm multiplying by P transpose. So my new matrix, okay, will be PT times B, because this is the transformation, okay? This is a change of variable. So each of those entries in that original table, in this table, each of them multiplied by P transpose to get new entries. So what happened to the covariance matrix here? The new covariance matrix will be 1 over n minus 1, okay, of this guy times the transpose of this guy. Now here, this where diagonalization is good, because I am going to have this. This one will be B transpose, and then P transpose, which is P. So this 1 over n minus 1 can be put inside, so it's P transpose 1 over n B transpose minus P. So we have PT. But what is this? Okay, this guy is my S. Okay.
Professor?
This guy is just, yes, I am writing outside again.
Yeah, thank you.
Maybe I should zoom. Yeah, no problem. So this guy is going to be the same as D, because S equal to PD B transpose. So D will be B transpose DP. Okay, so this is just D. So what did we do here? We have a covariance matrix. Okay, so after we transform the data, okay, so basically what happened is the following. You have original data x1, x2. You under this transformation, you get to y1, y2. Okay, so now this covariance matrix is going to be original covariance matrix is my S, and now it's D. So the new covariance matrix of D, that means, now remember D look like this, right? D look like the eigenvalues. D is the eigenvalues, which is 123, 102, and this is 1.98. So now these variables y1 and y2 are not correlated anymore. Because the covariance is 0. Okay. Am I still writing outside the thing all the time? Maybe I have to adjust this. Okay. So these two guys are not correlated anymore. So with this new variable, okay, with this new variable, what happened? The picture is the following. The original data is x1, x2. Okay. So you have a bunch of points here. Okay. So you have these new guys, these new directions is y1 and y2. y1 and y2. Okay. In these new directions with y1 and y2. So the direction y1 explains most of the variation in the data. All the variation in the data are going to be in this direction. And that direction is the direction of the eigenvector. Okay. This is the direction of V1.
How can you explain why most of the variation would be
Okay.
in Y1?
Okay, I will explain it. So the variation, because the variance, this is a variance for Y1, this is a variance for Y2. Okay. So the total, this 123.02 is a lot bigger than 1.98. Did I answer your question? So most of the variation are actually on this direction. Okay, and this direction is very small. Okay, so you can actually base on this. Okay, so basically this PCA, principal component analysis, is trying when you collect a bunch of data, you want to know a linear combination of your original data, okay, which explain as much of the variation as possible. So here, this explains most of the variation. Actually, the percentage explained is 123 divided by this total, which is about 90%. 90% of the variation is explained in this direction. Because when people have a higher weight, they usually are taller. Okay, so all the variation, okay, are mostly in this direction. And this direction, the variance is only 1.98. Okay, so you can actually have this thing called a size index. So size index is going to be your Y1. Okay, size index is your Y1 here. So this one is your size index. Because once you compute this, you already get most of the variation in the size and weight, all explained in this. But what is this? These coefficients are just direction of the eigenvectors. They're just direction of the eigenvectors. These are the other direction. The other direction doesn't have that much variance. I don't know, this may be a little bit not too easy for you to follow because it has a little bit of statistics in it. Okay. So I am going to talk about how the people generalize it to other applications. You have any questions? In other applications, here's another application.
Actually, I have a question about the page prior to that.
The what? The page prior to this?
Yeah, that one.
This one?
How did you, why is the new matrix P transpose B? And then how did you get to the next step after that?
Okay, so because I have this transformation, right? I have this, I do this change of variable. Any pair x1, x2, weight and height, okay? I will change it to these numbers, okay? So originally, I have a bunch of this way, this guy, the deviation, okay? X1 and X2 are not exactly the weight and height. It's a deviation from the mean for the weight and height. It's these numbers, okay? These numbers here are the weight and height, okay? The deviation from the mean, okay? So I need to change these numbers. So these guys are the X1s and X2s, okay? These guys are the X1s and X2s. I want to change it to the Y1 and Y2. So when I change it to Y1 and Y2, I do this change of variable here, okay? P transpose times X. So which turns will be these equations. So what I do is that I take my original set of data, which is this B here, okay? B is this rectangular matrix. B is this rectangular matrix. I multiply it by the transformation to get my new set, a new B basically. It's a transformed B, okay? Is it okay?
Okay.
For that part. And then I have to have this new B now. This new B, I need to find the covariance matrix. So it's 1 over n minus 1 times this matrix times the transpose of this matrix. Okay, so here this is just manipulating matrix here. Do you want me to walk you through this again?
Covariance matrix, is that the eigenvalues?
No, covariance. In this case, on the next page, I show you that it becomes the eigenvalues. on this next page, okay, it is the eigenvalues, okay. D is the covariance matrix, which only has the eigenvalues. So the eigenvalues have significance. The eigenvalue is the covariance of the transform variable. And the eigenvector is the direction of those lines. Which direction give me the explain most of the variations. Did I somewhat answer your question, or you want to follow up with another question?
I'm not sure if I don't understand the linear algebra or the statistics, but if I don't understand the statistics, then we can
Yes,
just move
that
on.
is part. Okay. Yeah. Okay. Yeah, I figure the statistics part is going to be slightly difficult because of the concept of covariance. But essentially, what it's trying to do is to use the diagonalization, okay, the change of variable, okay, so that all the variance, so you find the direction, which is a linear combination of the original variable, which explain most of the variance of the data. When I say most, it depends on the size of how big the eigenvalue is. So you can do this in general, you do this, you order the eigenvalues. The eigenvalues have different magnitude. The biggest eigenvalue is the one that explains the most variance. Because all those eigenvalues are the variance of the transformed variables. Okay, so I want to talk about the same thing here, except in this case, we are talking about facial recognition. We're talking about facial recognition. So instead of just weight and height, so you have these pictures of faces. And each of this is going to be, just imagine that it's 100 by 100 pixel. Okay, so all these are pixels. I mean, each pixel is like some grayscale. Let's say grayscale is like 256 levels. If it is color, then it has more. So all these pixels here, you line up this pixel so that it's linear. The first column is one entry, and then you just keep lining them up. So basically, all these things you line it up as one vector. So each vector, okay, has 10,000 entries. Each vector has 10,000 entries. So we are talking about in 10,000 dimension. In this 10,000 dimension, you have all this, each 10,000 dimension vector is going to represent one picture. Then you're going to take the average of all those pictures, subtract the average, get the covariance matrix, do the diagonalization, get all these eigenvalues and eigenvectors. So it will be 10,000 eigenvalues and 10,000 eigenvectors, and look for the biggest ones. Okay, and those biggest ones are the ones that characterize the face. The one with smaller eigenvalues, you can actually drop all of them and throw them away. Just zero them out. It's not going to affect the actual picture that much. Okay, so you can reconstruct the picture by throwing away a lot of the smaller eigenvalues and eigenvectors, because those doesn't really contain much information. So instead of storing, for each person, you store 10,000 entries. Now you can store maybe a couple of hundred entries. So I want to, I know this is a little bit hard for most of you because of some of the statistics. I want to play the video that I put in long time ago. at the beginning of the semester about these eigenfaces. It's exactly this application. So maybe you can appreciate that a little bit more now. That the video is only 4 minutes. Okay. So I'm going to try to play that. And after that, I will open this up. So I need to, what do I need to do? I need to stop share. I need to share again. I need to share my desktop. And I need to go to, you see my desktop now?
Yes.
Okay.
How come you would throw away some of the smaller eigenvalues?
Because the changes are not reflected there. They are very small changes. Okay, if you need to reconstruct the whole thing, you can just zero them out. Okay, because you're taking the linear combination. Okay, when you take the linear combination, so those, because of the bigger eigenvectors, so whatever you do, I have to probably go back to the other setup to explain to you. But basically, you can think of it as the smaller eigenvectors does not have as much information in it. Okay, so all the various, let's say if the number that I have earlier all lie in a straight line, all weight is always proportional to height. Okay, then you don't really need the other one, because then the other one, the eigenvalue will be 0. Okay, and then because the eigenvalue is 0, it doesn't really contain any information.
Oh, okay.
Yeah, hopefully I kind of explained it a little bit. I know it's hard, but I just want to show you this. Since we have a little bit of time, I want to show you this application, because at the beginning of the semester, I kind of promised you that at the end of the semester, you would kind of understand this. Oh, this is not the correct one.
Let's apply this to face recognition, and it's referred to as using eigenfaces. And it comes from this paper by Matt Turk and Alex.
Are you guys able to hear the audio and everything? And
Yep.
see the video?
Yeah.
Okay.
Sandy Pentland. It's Alex Pentland, but his name is, he goes by Sandy. They were at the MIT Media Lab at the time. And one of the reasons this paper, besides the fact that it works so well, is just known so well, in my humble opinion, is because of this term eigenfaces and face space. What a great phrase. In fact, I can show you the eigenfaces. I will in just a minute. All right. So here's what they do. They assume that most face images are going to lie on some low dimensional subspace in the big image space, determined by, I don't know, let's say K eigenvectors, okay, K directions of maximum variance, where K is going to be way smaller than D. So D might be 10,000 or a million. K is going to be like 20 or 200. Both of those numbers are way smaller than 10,000 or a million. So what it does is they use PCA, like I just showed you, to find the vectors, or what are called the eigenfaces, we'll look at the minute, U1 through UK, that span that subspace. Okay, so you take all your images, you find your eigenvectors. And now what you're going to do, and this is the really cool part, is you're going to represent your face images in that data set as just the linear combination of those eigenvectors. Or another way of saying it is, I'm just going to have the coefficients of, if it's 20, of the 20 eigenvectors, if it's 200, 200 eigenvectors, and I'm going to represent my entire image, all 10,000 numbers, by just the coefficients of these eigenvectors, and I multiply those coefficients times the eigenvectors, sum them up, that would be my new image. All right, so it's a tremendous data reduction. So take you through an example here. So, and some of these images come directly from the old papers, some from some newer work, but makes the same point. So suppose I have some training images, x1 through xm. So here's a picture of faces. Now notice it's just the cropped part of the face. So they're going to try to do recognition just on the cropped part of the face. So the first thing that's kind of cool to look at is this is the mean image. Mean face, not the mean face, the mean face, the average face. Now, nobody wants to have the average face. Too bad. Whoever that is, he or she has the average face. Why did I say he or she? Well, by definition, it's hard to tell, right? Because it's an average over everybody. There is some interesting work done on showing how average faces appear more beautiful than real faces. This was done a long time ago. It was just a study of the appearance of beauty. Anyway, it was an interesting image processing approach to thinking about, could you predict when a face would be deemed beautiful? And you can imagine, here's a question, show a picture to a computer, face image, pardon the digression, and say, on the average, on a scale of 1 to 10, how likely are people to rate this thing as beautiful, this person as beautiful? And could you do that? I think these days, using machine learning might be a different approach, but at the time, there was work done on looking at average faces. Sure you wanted to know that. Anyway, oh, and so what do you do with the mean face? Like what you should do with a mean face, you throw it away. Well, what you really do is you subtract it out of your population. Isn't that great? We subtract all the mean faces out of the population. No, we subtract the mean face from all the, and what we have left is our distribution. And then we start computing the eigenvectors, and here they are, okay? So here are some top eigenvectors. And one of the things you'll notice right away, in fact, let's take a look at this first eigenvector. Actually, the second one, is that it's much brighter on one side than the other because some of the variation might just be due to the lighting coming from one side or the other. But later, you have these different eigenvectors, which look like these kind of ghostly images. But these are eigenvectors. So they look to you like pictures, and they are. But what they are is they're a 10,000 dimensional vector, which is just an image. Remember, I can go between the image space, 10,000, right, and the images. So I'm just showing you these eigenvectors as images. Okay? And if I want to take a dot product of a real picture and these, that's easy. All I do is overlay them and multiply. Multiply every pixel and sum them up because that's what a dot product is. So when I show this to students, sometimes they don't understand how come the images are eigenvectors, and that's because in image space, that's what it means. A vector is an image.
Okay, so that is that video, and I don't mean to overload you guys with too much stuff, but I mean, I just feel that it's probably cool to see some application. Okay. So I'm going to open this back up then, okay? I'm going to open this back up, and you guys can ask questions and about when you study. And oh, by the way, you saw my the study guide a long time ago, right?
Yes.
So you guys, I assume you have been studying, and so what? You guys have any questions in general about the class? And I'm not going to teach you anything new anymore. I know that what I did already was so was pretty heavy, okay? But I just want to show the application. So how do you guys want to use the rest of this semester, which is about 2 hours? Not today. Today is half an hour and another hour or so on Wednesday. Tell me what you want to do.
I have a question from our second test.
Okay.
Specifically, let me open it up question 8 that was asking.
Okay.
You gave us a Markov chain.
Okay.
Do you have it with you? Or do you want me to share it?
I probably know which one you are talking about.
Okay.
I can open it up and share it. Okay. Second test.
Yes. Question number 8.
Second test. Test 2. I see. Are you guys seeing my desktop?
Yep.
Is this a correct problem, Josue?
Yes. Yes.
So which part? I mean, the part A is pretty straightforward, right?
Yes. Specifically, part B and C. I feel like
Okay.
part B is similar to. You asked us which question was it?
Okay. So
This is-
I'll go through this with you. Okay.
Okay.
I'll go through this with you guys. Okay. Let me kind of write down the question first. So what is the best? Okay. I'm just writing some more this down. Okay. Let me go back to the other setting then. Okay. So so you get a lambda equal to 1, you get eigenvector V1, right?
Yes.
It's when you get eigenvector V2. I'm not going to explicitly compute it. Okay.
Okay.
So you know how to do that.
Yes.
Then you just do x0 equal to express this guy. Okay. X0 as a linear combination of those two guys.
Yeah.
So you can have C1 V1 plus C2 V2.
Oh, okay. Okay.
Okay. So this V1 V2 is actually, you can think of it as P. It's similar to what we have done a number of times. Okay.
Yes.
That one would be V, would be P. And over here, that means this guy is going to be equal to P times C1, C2. So C1, C2 will be just P inverse of X0, okay, which is P inverse of this guy. But P inverse, you can compute P inverse because you already know P. Or you can just solve this guy, or you can just solve this system, okay?
Okay.
You can solve this guy, you can solve P C1, C2 equal to 1, 0, okay? And then
Okay.
you have this matrix P1, 0, and then do RREF, and that will give you your C1, C2. Are you with me?
Yes. Okay.
Okay, so once you get your C1, C2, some numbers, okay, then you have xk equal to ak. Xk will be ak x naught, okay, which means that you just keep doing it, so it's ak minus 1. Now x naught is, okay, x naught is what? X naught is c1 v1 plus c2 v2, okay, so this one you can just multiply it in, so you have c1 ak v1 plus c2 ak v2, but every time you multiply by a, you just
raise your
become
paper.
lambda, right? So this is lambda 1k v1.
Can you raise the paper? Thank you.
Okay, sorry. I probably need to, I just don't really know how to do the setting. I probably need to zoom it back out a little bit. Yeah. Lambda 2k v2. Okay. So this is basically it. This one is, you now C1, C2 you determine. Lambda 1 is equal to 1. Okay, but 1 to the power k is just 1, right? So that guy disappear.
All right.
C2 0.7 to the power k v2. Now all these are known. All these are known.
Okay.
And then you combine them into, you can combine them back into 2 entries. Okay.
Okay. I'll give that a try. Thank you.
Is it okay?
Yes. Just gonna try it out now.
I have a question.
Yes.
How come again you can change the a to lambda? Because it's multiplied multiple times.
Yeah, because a v1 is lambda 1 v1. So a square v1. A square v1 will be just a times a v1, right? So it will be a times lambda 1 v1. Will be lambda 1 a v1. Will be lambda 1 v1. Will be lambda 1 square v1. Is it okay? So each time you do a, multiply by a, you will multiply by lambda.
Okay. Okay.
Is it okay, Jose? Each time you multiply by a, you multiply by lambda.
Yes. Okay. Yeah. I wrote that down. Okay. Okay.
The same thing can be done through diagonalization also, it's just a different language. It's essentially the same thing. You could have, this problem, you could have done it in a slightly different way if you want, okay? You can write, you can do this if you want. If you want, you can do this. If you want, what you can do is that you have the a, all right? And then you can just diagonalize a. Diagonalize a. If you diagonalize a, so a will be P inverse, right? So then you have ak x naught, which is xk. Okay. So this guy will be.
Okay.
P inverse to the power k x naught.
Yeah.
Okay. You can look at it like this too. It's essentially the same thing. So this one will be P d to the power k P inverse x naught. But d to the power k is easy. D to the power k is going to be 1 to the power k 0.7 to the power k 0, 0. P inverse x naught. Is it okay? So this will be a slightly different, but it's essentially the same thing.
Okay. Yeah, I see it. Oh man, that was easy.
You can look at it either way.
Yeah. Oh man.
They are basically the same thing.
How would you know to or think to diagonalize A?
Why am I diagonalizing A? Because I know that if I diagonalize it, when I have this d to the power k, it's a lot easier. I know that, okay, first I know that this, right? I know that this guy is equal to a to the power k x naught. And if my goal is to find this, I need a general expression for this. In order to compute a to the power k, it's difficult to compute because it's not diagonal and it's not a diagonal matrix. But if I diagonalize it, it will become this to the power k. And this will become this. And then this one is easy to raise to the power k.
Okay.
Did I answer your question?
Yeah, thanks.
No problem. So any other things you guys want to ask or a particular topic you want me to reveal?
Will you be posting the answers to exam 2?
I wasn't really planning to.
Okay.
Yeah. But I can, if you have question, I can answer that.
I do have another question.
Okay.
Specifically on the same test, number 10. Where is it?
The same test, test 1 number 10.
Yeah, test number 10. Same test. Where is it?
Okay. So here's the question. Test 1.
Test 2.
Huh?
Um,
Test. Oh, you talk about test 1 or test 2?
Test 2.
Test 2. Okay. Let me pull that up first, okay?
Okay.
Because that was the one that I pulled up earlier was, oh, the one I pulled up was test 2.
Yes.
Oh, okay. 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 So the question is, if A is a square matrix, with the property that sum of each column is 3, then AX equal to 3X has a non-trivial solution. Okay, I copy down the thing. Are you guys still seeing my desk, my paper?
Yes.
Okay, so that's the question, right?
Yes.
Okay. What is the best way to do this? This has to do with Markov chain a little bit. It's related to the Markov chain. Okay. In the case of Markov chain, the sum of each column. In the case of the matrix for Markov chain, it's called probability matrix.
Okay.
Then the sum of each column is equal to 1, but now I change it to 3. So sum of each column.
Let's see the relation now. Okay.
So it's related to that. It's similar. So in the case of a probability matrix, the sum of each column is 1.
Mm-hmm.
And AX equal to X will have a non-trivial solution. Now I just change it to 3. So I mean, how to explain this? How to explain this is the following. I think this is my matrix A. Okay. Sum of all the columns is equal to 3. Okay. That means if you consider, now when you try to solve for this, when you try to solve for this,
Zero, yeah.
will be a minus 3I
Identity, yeah.
equal to 0, right?
Yeah, we gotta throw in an X in there.
So if I have a minus 3I, when you solve this, okay, then you are looking at this matrix. This matrix has a minus 3I here, and it has a bunch of 0 here. You're solving this, right?
Yep.
You're solving this. Now, when you solve this, when you do RREF, what do you think is going to happen? Would you get a row of zeros? It will get a row of all zeros because if you add up all this, okay. So for this matrix here, sum of all columns will be what? If you add up each column for this matrix, A minus 3I, you add up all the columns, what will you get? Without the 3I, it will add up to 3.
3, yeah, okay. Oh.
With the 3I, you're subtracting 3I. What will be the sum?
Is it 0?
Can you see it's 0?
Yeah, okay, yeah.
Can you see it's 0? Because for the identity matrix, each column you add it up to 1, right? So for 3I, each column is also add up to 3. So A minus 3I, sum of all columns equal to 0. That means when you do RREF, you have a row of all 0.
Mm-hmm.
When you have a row of all 0, can you have pivot in every row?
No.
You cannot have pivot in every row. So the original matrix A, so A minus 3I does not
Have a non-trivial solution.
have pivot on every row.
Oh, what did I write?
It doesn't have pivot on every row.
Right.
It also means that it does not have any pivot on every column because this guy is a square matrix.
Mm-hmm.
Because that guy is a square matrix, we will not have a pivot on every column. When it doesn't have a pivot on every column, that means when you solve this guy here, you are going to have a free variable.
Yes.
And that will provide a non-trivial solution.
Yeah. Okay. Let's see.
For this problem, would you have to say that there's not a pivot on every column, or could you just say there's not a pivot on every row?
You have to say there's no pivot, it does not have a pivot on every row, and because A is a square matrix, then A minus, so this does not have a pivot on every column. So it's that's the logical step. So you actually have to say all that. Because it doesn't have a pivot on every row, and because A minus 3I is a square matrix, it will not have a pivot on every column. And because of it doesn't have a pivot on every column, there will be some column which correspond to a free variable. And because of the free variable, then this equation will have a non-trivial solution. That in some sense, that means 3 is an eigenvalue. So when they grade this problem, some students say that, give the reason that they say that this guy has a non-trivial solution because 3 is an eigenvalue, and that is not an explanation. That's just restating what I want you to prove. You know what I'm saying? So any other things? So Josue, is it okay, or you have any?
Yeah,
the-
I gotta think about which step is it. A minus 3i, the sum of all columns is equal to 0. That's the part I still don't see, but I'll think about it and come back.
Okay, so for the identity matrix,
Right.
Josue, for the
Mhm.
identity matrix, okay, what is the sum of each column
The identity, 1,
for the identity matrix?
1.
You understand that, right? You agree that.
Yes.
So for 3 times the identity matrix,
Sum is gonna be
3i.
3i.
So the sum of each column will be 3.
Yes.
Okay, so for a minus 3i, because the sum of the columns for this guy is 3, the sum of the columns for this guy is also 3. So when you do the subtraction, the sum will be 0. No? Yes?
No, I don't see that. I get the math, but I'm not.
Okay.
Can you? Oh man.
I can draw it out for you if you want.
Yeah, that would help me.
So you have 2 matrices.
Minus 3 across the diagonal.
This is a matrix B. Okay.
Okay.
So the sum of these entries
All right.
are
3.
going to be 3. Okay. The sum of these entries are also going to be 3. Okay. So now the difference, this matrix, when you one matrix subtract the other, means that this will be A11 minus B11, A12 minus B12, A13 minus B13. You're just subtracting the corresponding entries, right?
Right. Okay. And
Can you see that?
Yeah.
When you, okay, I just have to write out all this. So when you look at this guy, the sum of these entries here, so this 3 is going to add up to 3. This 3 is going to add up to 3. When you subtract them, it's going to be 0.
Okay.
But like, why? Oh no, I'm confused.
I feel like I'm confusing my
It's okay.
matrix.
The sum of each row equal to 3 means that these 3 entries add up to 3. Okay, so this is my 3i, also add up to 3.
Yeah. Okay. I think what's confusing me is because we know it's 3i, so it's going to be A11 minus 3. Then A22 minus 3.
So, okay, so another way to do this is that because it's 3i, right?
Right.
So, okay, this one is this is the more general way. Let's say that this is A then, okay? So
Okay.
A minus 3i will be A11 minus 3,
Yes.
A22 minus 3, A33 minus 3. The other entries remain the same.
Yes.
Okay. You add this out. Add these 3 entries out. When you add these 3 entries up, this is going to give you 3. And 3 subtract 3 is 0.
Yeah, okay. Now I see it. There it is. Okay.
It's okay?
Yes. Yeah. A21 and A31. The sum of that is gonna be, yeah, okay. A11 minus 3, they cancel out, 0. Okay. I
It's
see
okay?
it. Yes.
Okay,
Thank
good.
you.
Good, yeah. I want to use symbols. I want to just, I mean, I try to avoid proving this by example, but with an example, it's easier for you to see.
I see it now.
Any other thing?
I have a question if no one else does.
Okay.
How
Okay.
come the determinant of a matrix has to equal 0 in order for it to have a non-trivial solution?
Okay. Determinant of a matrix. I see.
Can you repeat your question?
Why does the determinant of a matrix have to equal 0 in order for it to have a non-trivial solution?
Oh, okay.
Right? This is what you're asking.
Yeah.
Okay. So, okay, I have 1 minute. Okay. So, number of ways to this. Those elementary row operations. Okay. The elementary row operations, you remember, you know what I'm referring to? The swap,
Yeah.
the scale, okay, and the replacement. Okay. So if I have a matrix A going to a matrix B, when I swap rows, how are they related? Determinant B and determinant A. When I swap two rows, what happened to the determinant?
Negative?
Yeah.
Negative. When I scale, let's say scale by K. Scale one row by K, okay? Scale row by K. Then determinant B is going to be K times determinant A. Scale this by K and K is not equal to 0. The other one is replacement. What happened to replacement? What does it do to the
Nothing.
It's the same.
same? It's not negative, it's the same. So basically, okay, if I have two matrices, if I have two matrices, A and B, okay, B is row equivalent to A. Okay, so determinant of B is equal to 0 if and only if determinant A is equal to 0. Because all those three operations, one is changing it to negative, one is unchanged, one is scaling it by a non-zero. So basically, row operation doesn't change whether if it is all doesn't really change whether the determinant is 0 or not. It may change the value, but if it is non-zero, it remains non-zero. If it is, and vice versa. Okay. So these row operations So when is this guy? When is this guy? When does this guy has non-trivial solution? This guy has non-trivial solution if there are not enough pivots, right? You
Right.
agree?
Yeah.
If there are not enough pivots, okay? But the A is square matrix. A is square matrix. If there are not enough pivots on the columns, that means there are not enough pivots on the rows. Okay? That means there will be a row of 0. The RREF will have a row of 0. So that means if this guy has non-trivial solution, okay, then A has a row of 0 in its reduced row echelon form. Okay. So if it has a row of 0s in its reduced row echelon form, okay, that means that the RREF, let's call it B. So if you have a row of 0, that means the determinant of B is equal to 0. Because if you have a row of 0, you compute the determinant, it's going to be 0. You can expand along that row. So because this determinant of B equal to 0, that means determinant A is also equal to 0. Is it kind of okay?
Yeah.
I think I answered your original question. Yeah. It has to do with all those reasoning.
Okay. So
Okay, we already at 2:05. So you guys think about what you want to do on Wednesday. Okay, I don't have anything in mind. Okay, I hope I didn't overwhelm you too much with the first 45 minutes about this application, but I think that it's probably kind of cool to see the application.
it was good.
Okay. All right. So anything else?
Professor, could you open up the submission trial thing? I want to see if I could, if I found a new way, if I could submit the test faster than before.
Okay, I will do that. I will do that.
Thank you.
Okay, open try. Okay, it's closed now probably. Okay.
Thank you.
Okay. Okay. Thank you, guys. I appreciate you coming to class.
Thank you.
Thank you.
Bye, Professor. Thank you.
Thank you.
So how many people I have today? I don't have that many people. Okay. See you guys. Bye. How do I end this? Okay.